This is Math 139, Section 1.2, Part A. We're going to be looking at some things that graphs can tell us about functions. But before we get there, we need to start with a little bit of background work on something called interval notation. Turns out, interval notation, which is just another way of writing inequalities, is often very useful when we're trying to describe sets of numbers. A set of individual values can be listed, for example, 1, 2, 3, etc., up to 10. But what if I wanted to include all of the numbers between 1 and 10? The fractions, the decimals, 2.7, pi, all of those numbers. In order to do that, one way to write it is by using our inequality notation. This is my inequality notation that says all of the numbers between 1 and 10. Another way to write the same thing is what's called interval notation. The interval notation for that same exact thing looks like this. It's the numbers from 1 to 10, and then we've got some special symbols here, the bracket and the parenthesis, that we'll talk about a little bit more in just a minute. In this next little set of examples, I've given us some inequalities to work with. We're going to take a look at what they'd look like if we tried to plot the solutions on a number line, and then we'll also write the interval notation. So we'll start with the numbers from -1 to +3. Going from -1 to +3, and I want all of the numbers in between, so I show that just by drawing a line there. To write the interval, I always list my values from left to right, so I'll write that as -1, 3. And notice, it's not just less than signs here, it's actually less than or equal to signs. The way that I show that in the interval is with these brackets. The brackets really mean include the endpoints, include the -1 and the 3. All right, in our next example, we'd like to look at all of the x values between 2 and 5. But notice this time we're not including the 2. There's no equal sign on this less than, but we are including the 5. This one is a less than or equal to. I show that on my graph by starting with an open circle. That means I can get as close to 2 as I want to, but I can't actually touch it. My x is never actually equal to 2. I keep going until I get to 5, and I can equal the 5, so I'll use the solid dot there again. And then I wanted all the numbers in between, so I just connected them with a solid line covering all the fractions and decimals in between. To write my interval notation, once again I want to go from left to right. So I'm going to go from 2 to 5. Using the interval, I show that I don't include the endpoint at 2 by using a parenthesis rather than a bracket. I do include the 5, so I'll put the bracket there. So the parenthesis means don't include the 2. The bracket means do include the 5. All right, the next one. X is greater than -2. There is no equal sign here, so down here at -2, I'm going to start with an open circle. Can't include that -2. Now I want the x's that are greater than, bigger than that -2, and I don't have any stopping point. I just keep on going forever. So I'm going to show I want to be bigger than negative 2, and I'll show that it continues forever with a little arrow on the end of my line. When this happens, we want to imagine that we're going out forever or towards infinity. Mathematically, infinity is not actually a number, it's more of a concept, but I'll just sort of show the infinity as what we're heading towards, just to help us write the interval. So I'll begin at negative 2, with a parenthesis since it's not included. And I really don't end, but I show that by saying we're headed towards positive infinity. I have to use a parenthesis with that one too. It's never possible to actually reach infinity. We can't really get there, so we'll never have a bracket on an infinity. All right, one more little practice with intervals, and then we'll put them in context. This time I want x to be less than or equal to 4. So I'll begin at the 4 with a solid dot this time, since it's less than or equal to. And this time I want my x to be smaller than that. So I'm going to go to the left. Just like the right-hand side we think of as heading towards a positive infinity, a left-hand side that goes on forever heads toward a negative infinity. Be a little careful when you're writing intervals here. Again, we always write our intervals from left to right. It doesn't matter what direction the arrow is pointing. So when I write this interval, the left side is at negative infinity, and the right side is at 4. Again, I can never really reach negative infinity, so that has to be a parenthesis. But I do include the 4. I do reach the 4. So I'll use a bracket there. One more time, just as a reminder, we always use parentheses with infinity and negative infinity, because we can never really reach them. All right, we'll use interval notation frequently in this class, and one of the things that we can do with it right away is go back to our idea of domain and range. And when we had domains and ranges that were a whole group of values, we can sometimes write those with interval notation. So let's take a look at a couple of examples. On the next page, I'm going to start with this function defined by this mapping diagram. And in this case, notice that we don't have a whole infinite set of values. We only have specific individual values for our inputs or our domain and our outputs or our range. So this time I'm going to just list them. The domain is the specific numbers, -5, -4, -3, and -2. Notice these braces, again, indicate just those specific values. I have not used interval notation because I don't have all of the fractions and decimals between those values. Similarly, in the range, I only have the 3 individual values, 0, 1, and 3. All right, what about this next one? F of x is equal to -5x plus 8. What is the domain? Well, the inputs are the values of x that are okay to substitute. Can you think of any value of x that you wouldn't be able to calculate this function for if you substituted it in? I can't. X can be anything. I can plug in negative numbers, positive numbers, fractions, decimals, 0. They're all okay. So in this case, I'm going to say my domain is all real numbers. A convenient way to write all real numbers is to use interval notation. I can say it's all the numbers from negative infinity to positive infinity. And I will use those parentheses on my infinities. I can use sort of the same argument for the range. Remember, f of x's function notation is just like y. And when I think range, I think about the y values. Are there any numbers that wouldn't work for y? I can't think of anything. No matter what number I put here, I could always solve for x just by subtracting the 8 and then dividing by the -5, and I'd get an answer every single time. So I think the range is also all real numbers. Or in our interval notation, all the numbers from -infinity to infinity. All right, what about our next function? Y equals the square root of x. Are there any numbers in the domain, any numbers that would be a problem for the domain, anything I can't substitute for x? Well, in this case, since I'm trying to take the square root of x has to be a positive number to start with. I can't take the square root of a negative number, at least not without getting an imaginary number as an answer, and we're going to assume that for right now, we're just working with real numbers. So as far as my domain, I'm going to have to think x greater than 0. Now let's think for just a moment about the 0 itself. Can x equal 0? Well, the square root of 0, yeah, that's just 0, isn't it? So I think we can actually say greater than or equal to 0. That means that my x values can go from 0 to positive infinity. What about the range? What about the y values? Well, when you take the square root of a number, you always get a positive answer. The square root of 9 is 3. The square root of 16 is 4, and so on. So I think y is also positive. And kind of the same argument as before. If I did let x equal 0, then y would be the square root of 0, which is also 0. So we'll include the 0 here as well. And my range also goes from 0 to infinity. All right, so those two examples had functions defined by equations. The next one, we're back to the function being defined a different way, in this case by a set of ordered pairs. And notice here, we do not have all of the numbers, fractions and decimals, etc., in between a couple of values. Instead, we have very individual and specific x and y values. So I'm going to use the listing method here. The domain are all the x values, 1, 2, 3, 4, and 5. And y's are all the second values of the ordered pairs. We'd have 4, 6, 8, 1, and 6 again. Let's see, I like to put them in order, so I'm going to list it as 1, 4, 6 happens to occur twice, but I only have to put it once in my list, and 8. So no interval notation here. We only have specific individual values for the x's and the y's. All right, last example, we're back to an equation form of a function again. Y is equal to x squared plus 5. And starting with the domain, I want to think about what x values are okay to plug into that equation. In this case, I think anything. I can square any number, a positive or a negative, a fraction or a decimal, 0. It's possible to square any of those before I add 5. So I believe all real numbers is once again going to be my domain. In interval notation, that means I'm going from negative infinity to infinity. What about the range? We're going to see in the next section, this is actually a little bit easier to see graphically. But this time, let's see if we can talk ourselves through it. kinds of numbers are the y's? Well, when you think about x squared, no matter what number you square, you're always going to get a positive result, or at least 0. So if I've got a number that's 0 or bigger than 0, and I add 5 to that, I've made my number larger than 5, or if it's 0, equal to 5. So I think all the y's are going to turn out to be 5 or bigger. Greater than or equal to 5. In interval notation, that means I would go from 5 to positive infinity. All right, so we've got our section 1.1a complete.